Hello, Physics 1. Welcome back. Part 2 of Monday's lecture last week. Oh my goodness. How long have we been online? Is it 600 years, 700 years? I don't even know anymore. All right, so we're still on angular momentum. Moving on to section 11.3 in your book. Okay, so we know, because we studied kinetic energy, that the total kinetic energy is equal to the sum of the translational kinetic energy plus the relative kinetic energy. So translational is movement of the center of mass and movement relative to the center of mass. So if we throw a frisbee, we know that translational displacement, so just the arc that it makes, that would be its translational kinetic energy, and the relative kinetic energy would be the spinning motion. Okay. Angular momentum, so similar concepts work for angular momentum. Angular momentum can be expressed as the total angular momentum with respect to some point A being equal to the sum of the translational component with respect to A plus the relative component. So let's say we've got some point A, and we've got a center of mass here. And then we've got three molecules, or just points, that are all contributing to the center of mass. So you've got R1, R2, or actually make that R3, and R2. All right, so these are the vectors corresponding to their distance from the center of mass. We would also have this vector here going from A to the center of mass, so this would be our center of mass. Okay, each one of these would have some momentum associated with it, so we've got P1, P3, and P2. Okay, and then I'll make this really clear. This is the position vector relative to the center of mass. So when we're thinking about translational angular momentum, we want to think about where that spot A is located relative to the center of mass of this system, and then these contributing components here, maybe they're going around the center of mass, so we want to think about where they are located with respect to the center of mass. All right, so let's start thinking some things. So position, and so this is M1, M3, M2, in case that's not very clear. Okay, so position of M1 relative to A. So M1, we'd have R1 is equal to RCM plus R1 CM. So we want to think about the RCM, and also then what do you do? So you can see you're just adding these two vectors together. M2, as it would follow, R2 is equal to R CM plus R2 CM, M3, R3 is equal to RCM plus R3 CM. Let me just modify my picture. So these are all vectors with respect to the center of mass. Okay, so now we've got an expression for the vectors for each one of the mass components relative to this position A that we're using to find our angular momentum with respect to it. Okay, so we know how to calculate angular momentum. We know new vector operations. So we can use these vectors to calculate total angular momentum. Relative, so total angular momentum, so this would be capital LA, and this is all, of course, relative to that position A. So LA is equal to RCM plus R1CM crossed with momentum 1. So basically what we're doing is we're saying, okay, so the total angular momentum is the sum of all the parts. So we need to then apply the angular momentum formula repetitiously to get the sum of all of the parts. So, plus RCM plus R2CM cross P2 plus RCM plus R3CM cross P3. All right. Oh, excuse me. So this is equal to RCM cross P1 plus P2 plus P3. So all we've done here is we factored out this RCM component, which is unique to each one of these. And we see that it's going to be crossed with each one of these momentum vectors. And then we're not done with this equation yet. So plus R1CM crossed with P1 plus R2CM crossed with P2 plus R3CM crossed with P3. And so we know that P1 plus P2 plus P3 is going to be equal to the total momentum of the system. So then L angular momentum is equal to R CM crossed with P total plus R1CM crossed with P1 plus R2CM crossed with P2 plus R3CM crossed with P3. And what we've seen here is that actually our angular momentum formula has broken down into two very nice parts. We've seen this already. This is translational. And this side is rotational. So this is going to be the center, or all of the parts going around the center of mass. And so this is the breakdown between that, that's our expression for angular momentum. By the way, just an aside, here it is, rotational angular momentum is also called spin. So you'll hear spin from time to time. All that is rotational angular momentum. All right. Okay, so let's write out a couple formal expressions because it's always good to have our formal expressions. So total angular momentum LA is equal to L translational A plus L rotational, and translational angular momentum is calculated L translational A is equal to the center of mass, the vector from the center of mass to point A that you're looking for the angular momentum with respect to cross the total momentum. Woo! And rotational is equal to L rotational, which is, so L rotational is R1 CM crossed P1 plus R2 CM cross P2, so on and so forth for each component. So it's similar to what we saw with rotational energy. It turns out you can encapsulate these sums in the moment of inertia, but this is still a sum. So, and this is a cross product expression. So when I teach astronomy, what I often do is I open up lab time as a time that anybody in the class, whether or not they're taking their lab, will answer questions. And I'm often playing music because it really works with the astronomy lab to play music. And it can be really fun to answer questions with music on. And it makes me very inclined to try and see if I can make up songs about whatever I'm explaining as I go. And right about now, boy, do I wish I could be lecturing with some music. Although I'm not a terrible singer, but I'm not a great singer. So maybe you don't wish the same. Okay, so now that we know linear momentum, we talked about that if we want to change linear momentum at the beginning of the chapter, we need something called torque. That's the twist. So you're familiar with torque anytime you've if you've ever wrenched a bolt, you have applied torque to something. Every time you open a door, you're applying torque to the door in order to open it. Every time you drive a car, you are applying torque to the steering wheel in order to move your car. All right, so, and we talked about that change in linear momentum is related to torque. So we should introduce torque. All right, so the linear momentum can be changed from an outside force. And the force to change angular momentum is a twist or torque. Definition of torque. Of course, in physics, we often define things with equations. This will be no different. Torque is denoted with a tau. Once again, it's still with respect to a particular location is equal to r, the vector with respect to that location A, cross F. So once again, we see the cross product coming back. That's why we took the time to really teach it, is because once you know cross products, you see that there's actually quite a few cross products in physics. So torque, due to a force is defined at a particular location. So we want to know, where are you applying this force? So for example, think about it in terms of if you're opening a door. Is it easy to try and push the door open right by the hinges? Or is it easy to open the door closer to the handle, which is further away from the hinges? Where you're applying that torque to, that twisting motion to, is relevant to how much it's going to change the angular momentum. Okay, so more on torque. RA is the vector from A to a point of applied force. So let's see. All right, and the units of torque are newtons times meters. So, for example, here is RA. Here is our applied force. And so this is our RA. And then torque would be RA cross F. And once again, you can use the right-hand rule. For torque, you'd line it up with R cross towards F. So in this case, it's coming out, just as I wrote here. All right, so, and I've also drawn, so if you've got a wrench, I know, my amazing drawing skills on full display. All of these places would be more or less effective for wrenching it. You could also apply here. So if you wrench it really close to the bolt, that's a lot harder. So this would be more effective than this. This is more effective than that. This would be the most effective. Now, if you apply a force on the end of the wrench, I will tell you, you will not twist that particular bolt. So in that case, you're dealing with something that is not going to twist. It's parallel. So most effective would be right here. Totally ineffective would be this one. And these would be ranging in their effectiveness. All right, so where the force applies matters in torque. Okay, so far we have a vector expression. Now let's write down a scalar expression for the magnitude of torque. So torque is equal to the magnitude RA times the magnitude of the force times sine theta of the angle between them. So, for example, let's draw a little wrench out again. If we want to look at perhaps the torque, put part A, or position A relative to what you're trying to twist, then if you apply a force near the end, perhaps like so, then your RA would be right along here. Then we would have F cosine theta. This would be theta. And then F sine theta. Okay, so, and what we can see from here is that the angle of force matters as well. So where you're applying it and also at what angle makes a difference into how effective your torque is going to be at changing the angular momentum. So for a perpendicular force, torque is equal to RA times F. And for a parallel force, torque is equal to 0, which we've already implied. And this all has to do with that, the angle of sine theta. Okay. Also, it makes sense conceptually. Like, you're generally speaking, when you're trying to torque a bolt, you're trying to torque the wrench from as perpendicular of an angle as is possible. That's going to allow you to more effectively twist the bolt. And I should know, I once spent a month torquing bolts on a dark matter detector underground. I kid you not, we were doing 12-hour torquing shifts. I am dead serious. All right, the direction of torque. So you want to put R and F tail to tail. So in the picture we just drew, they were not tail to tail, but if we move RA over, we can fix that. And then you use the right-hand rule, line your right hand up with R. So in this case, if I line it up this way, I cannot naturally twist, so I need to flip it, line it up, twist towards F. Torque in this case would be in the negative direction, into the page. So use the right hand to line up with R and curl towards F. So just a note, nuts and bolts tend usually right-handed thread. So you would advance into the page. Which is exactly what we saw with this setup. So when we turn it here, we see we're going to be putting our bolt into the page. Of course, I will warn you that if you ever change out your pedals on your bike, if you want to switch to, say, clipless pedals, one side, I think your right-hand side is threaded in a right-handed manner, but your left-hand side is threaded the opposite way. So, not true across the board. But this is where we get the expression righty-tighty. And anyone who has ever worked with vacuum components, you are very familiar with bolting on flanges and taking them off. Righty-tighty, lefty-loosey. Are you advancing in? Are you advancing out? Okay, so let us do an example. I'm going to start a new page. See, there's practical applications for physics everywhere, like torquing bolts. Let's think about torque on a seesaw or teeter-totter or whatever you call it. So Esther, who at the time I wrote this problem weighed about 14 kilograms, and Piper, that would be my husband, sit at a distance (1.1 meters) from a pivot point. And we're going to ignore the mass of the seesaw. Okay. So, what is the net torque on the system of the people plus seesaw about the pivot? So the pivot is where you go back and forth. Okay, so let's draw some great pictures. So let's say Esther is over here. Piper is over here. Okay, so we would make this our A. So then this would be our PA. And this would be our EA. Now they have the same magnitude. They're both 1.1 meters away. And if we were to continue up with our force diagram, we would see that there would be a normal force pushing up from the pivot point and the force of gravity pulling Esther down. And there would be a force, excuse me, of gravity pulling Piper down. All right, so now we have a little force diagram, and to get net torque, we need to add up all the torque. All the torque. All of it. Okay, so torque due to Piper, then you would have torque of Piper relative to A is equal to R of Piper to A crossed with the force on Piper. So this is equal to 1.100 cross 0 minus 79.80. Pick your favorite way of doing a cross product. So you could do IJK, you could do the formulation, and then there's a couple other different ways to think about cross products or to solve them. You could also find the magnitudes of the vectors and multiply them by the sine of the theta angle between them and use the right-hand rule to determine. Doesn't matter. Whichever way, so choose your favorite way of solving cross products. Your favorite cross product technique. And show me in your work. And you'll get 0, 0, minus 754.6 newtons per meter. All right, so. All right. Next, we need the torque due to Esther. So torque from Esther relative to A is going to be the position vector from Esther to A crossed with the force on Esther. This is equal to minus, so remember she is in the negative x direction. 1.1 crossed with 0 minus 9.8. So force of gravity is going down, 0. And this is equal to 0, 0, 161.7 Newton meters. All right, so there's one other force we need to think about, and that's the normal force at the pivot point. So if we're going to get total torque, we need to look at all of the different forces. So for normal force, we have the torque. The normal force with respect to A is equal to the vector from the point of normal force A cross the normal force. Well, to get from A to the application of the normal force is you go no distance, so that's 0, 0, 0. So we have, this is equal to 0, 0, 0 crossed with 0, 85 times 9.8, 0 is equal to 0, 0, 0. By the way, this is often why you will choose a point like a pivot to be the respect or the position with respect to A that you're looking at angular momentum, because it gives you a really nice 0. Zeros can be really handy. Okay, so from here, we see the net torque is just going to be the sum of all the torques, which is equal to 0, 0, 0 from the normal contribution, plus 0, 0, minus 754.6, plus 0, 0, 161.7 newtons times meters. The total torque is equal to 0, 0, minus 592.9. On your own, verify sign using right-hand rule. All right, so that is how you do torque. So moving on. So now that we have an expression for torque, we can go after the angular momentum principle. Okay, so the angular momentum principle, L final with respect to A is equal to L initial with respect to A plus the net torque with respect to A times the length of time. This is the update form. Very similar to the momentum principle, that we would have the change of angular momentum with respect to A over the change in time is equal to the net torque with respect to A, which is the derivative form, likewise, you can also write that delta LA over delta T is equal to torque net A. And then we would have the conservation form, because angular momentum is a conserved quantity, just like regular momentum. So L A of the system was delta L A of the surroundings is equal to 0. So this would be the conservation form. And these apply to systems modeled as point particles. All right, so I think this is a good spot to stop lecture for Monday, and we'll resume on Tuesday, looking at the relationships between the angular momentum principle and the momentum principle, which we're more familiar with.